Welcome to Standard Enthalpy Changes. Thermochemistry is the study of the energy transferred as heat during a chemical reaction. The standard enthalpy change, which we symbolize delta H naught, is the enthalpy change for a process in which the reactants and products are in their standard states. Now, the standard state is the pure form of a substance at 1 bar at a specified temperature. The standard enthalpy change for a reaction is the difference between the products in their standard states and the reactants in their standard states, all at the same specified temperature. That is, we can show that mathematically like this, where we have the enthalpy change delta H for the reaction is equal to the sum over all of our products of the enthalpy of the product minus the sum over all of our reactants of the enthalpy of the reactant. For example, the standard enthalpy of vaporization, which we can show this way, for water, where note that we're going from liquid water to gaseous water, is given here. And now this is for the standard enthalpy of vaporization at 373 Kelvin. That's equal to plus 40.66 kilojoules per mole. Now, note that the standard enthalpies may be reported at any temperature. However, the convention is to report the thermodynamic data at 298.15 Kelvin, so 25 degrees C. And unless otherwise mentioned, Atkins reports thermodynamic data for this temperature at 25 degrees C, and we will use the same convention. So if we don't specify what temperature that data corresponds to, you can assume that we mean 25 degrees C or 298.15 Kelvin. Now, the standard enthalpy of transition, which we symbolize this way, is the standard enthalpy change accompanying a change of physical state. That is, we're transitioning from one physical state to another, one phase to another. For example, the standard enthalpy of vaporization, which we symbolize this way, is the standard enthalpy change accompanying the boiling of a liquid to a gas. The standard enthalpy of fusion is the standard enthalpy change accompanying the melting of a solid to a liquid. So if we melt from ice to liquid water. In this case, the standard enthalpy of fusion for water is 6.01 kilojoules per mole. And you should see table 2.4 for more examples of standard enthalpies of transition. We have lots of different transitions. Now note that while IUPAC recommends the usage that looks like this, where we have the transition abbreviation in between the delta and the H, the transition subscript is often attached to the H, so it looks more like this. And these two notations are functionally identical. You can use either one. You should also see table 2.3 in the textbook for standard enthalpies of fusion and vaporization for a few substances, for benzene, water, helium, and argon. Now note that the enthalpies are reported for the transition temperature, not at 25 degrees C or 298.15 Kelvin, except for the enthalpy of vaporization of water, which is reported for both temperatures. Now, I want to take a little bit of time and talk about how awesome science is. So helium-3 and helium-4 have negative enthalpies of fusion at certain temperatures. So the temperatures below 0.3 Kelvin and below 0.8 Kelvin, respectively. And this means that they give off energy upon melting. Now that's really, really bizarre. Because normally if you have something like water, if in its solid phase, so you've got ice, if you want to melt that, you have to put in energy. So that substance absorbs energy. Well, helium, if you have solid helium and you melt it, it's going to give off energy because it has a negative enthalpy of fusion. So, under the right circumstances, helium will freeze if you add heat to it. If you heat up helium under the right circumstances, you can actually get it to freeze. And that's just awesome. So recall that enthalpy is a state function, and thus a change in enthalpy is independent of the path taken between the two states. And this is very important in thermochemistry because it means that the enthalpy changes for each of these processes is equal as long as all the processes occur at the same temperature. So if we look at the sublimation, so going from solid to gas, that process is shown by this arrow here. We've got some enthalpy change. Now if we take a more roundabout process and we melt solid to a liquid water, and then we boil the liquid water to a gas, so we're doing this in 2 steps, we have 2 enthalpy changes, but the overall enthalpy change has to be the same for both processes. So that is, the enthalpy of sublimation at standard state has to be equal to the enthalpy of fusion at standard state plus the enthalpy of vaporization at standard state. Now this is occurring because in order to sublime our water, we have to break all of the intermolecular bonds between the water molecules and their neighbors. Well, that's essentially the same thing we're doing in this 2-step process. In melting from a solid to a liquid, we're allowing just a few of the intermolecular bonds to break. That allows the molecules to move past each other, but still stay all together in the liquid phase. If we then give those molecules more kinetic energy, so now we're breaking all of the intermolecular bonds, now we can boil the liquid water into steam. But breaking all of the intermolecular bonds is going to take exactly as much energy as breaking some of them and then later breaking the rest of them. So that means that the enthalpy changes for the 2 processes has to be the same. Also, the enthalpy change of the reverse of a process has the opposite sign of the enthalpy change for the forward process, but the same magnitude. That is, if we have some enthalpy change where the enthalpy increases, and then later in time we reverse that enthalpy change, we're going to get out exactly the same amount of energy if we return to exactly the same state. And that means that the magnitudes here are exactly the same. And it doesn't matter the path that we take from one to the other or back. It also means that if we go from one state to a different state and then back to the first state, the enthalpy must be exactly the same as it was before. So now let's talk about lattice enthalpy, or delta H L naught. And again, we could put this L in between the delta and the H if we wanted. The lattice enthalpy is the change in enthalpy for the separation of the ions in an ionic crystal to the gaseous state. That is, we have some ionic compound MX in the solid phase, and we're separating that to an M ion in the gas phase and an X ion in the gas phase. And it doesn't matter what the charges on here are. The lattice enthalpy can be calculated using a Born-Haber cycle, which is a closed path of transformation starting and ending at the same point. For example, if we're looking at potassium chloride, we can start out here with our potassium solid and our chlorine gas. If we then sublime the potassium solid to the gas phase, it's going to take 89 kilojoules per mole. And then from there, we dissociate the chlorine gas. So we go from Cl2 to Cl atoms. So chlorine molecules to chlorine atoms. It's going to cost 122 kilojoules to break that covalent bond. Next, we're going to ionize the potassium. So we're going to go from a potassium atom in the gas phase to a potassium ion in the gas phase. That's going to cost 418 kilojoules. And so now we have a potassium ion in the gas phase, we have an electron in the gas phase, and we have a chlorine atom in the gas phase. Now we're going to add that electron to that chlorine atom. That's going to give us back some energy, so we get out 349 kilojoules, so that's a negative enthalpy change. And now we have a potassium ion in the gas phase and a chlorine ion in the gas phase. And now when we combine those two, this is now the lattice energy. We're going to get a lot of energy out. And now we have potassium chloride solid. And then the last step we take is to return back to the potassium solid and chlorine gas. So we basically undo the reaction 37 kilojoules of energy. So now let's examine the combustion of methane. So we have methane, CH4, in the gas phase plus 2 oxygen molecules will react to yield carbon dioxide and liquid water. Now the standard reaction enthalpy, which we symbolize this way, is the change in enthalpy for a chemical reaction. In this case, the standard reaction enthalpy is negative 890 kilojoules per mole, where here the per mole means per mole of reaction. And note that 1 mole of reaction means that 1 mole of methane reacts with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water. Also note that the negative sign there means that we're getting energy out of our reaction. That is, our products have a lower enthalpy than our reactants do. And therefore the enthalpy change for the reaction is equal to the sum over all of our products of VI times the enthalpy HI, where VI there is the stoichiometric coefficient for the ith reactant or product, and VI is going to be dimensionless. It's going to be positive. So this is basically the coefficient in the balanced chemical reaction. So we've got the sum of the stoichiometric coefficient times the enthalpy for our products minus the sum over all of our reactants. Now some standard reaction enthalpies have special names and are of particular significance, such as the above standard enthalpy of combustion, which we can label this way. And this now brings us to Hess's law. The standard enthalpy of an overall reaction is the sum of the standard enthalpies of the individual reactions into which a reaction may be divided. So note that the individual reactions need not be real reactions. They must, however, add to give the overall reaction. So that was standard enthalpy changes.